Okay, so now let's move on. Let's talk about the photon model of electromagnetic waves. We're going to talk about a number of different models of light as we go through this semester. Well, we have two more. A number. That number is 3. We're going to talk about the photon model today. We also have the ray model and the wave model. We'll talk about those more here in a couple weeks. The photon model of electromagnetic waves. This is where things start to get really weird and really interesting. As far back as folks have thought analytically about what light is, folks have argued about what the fundamental nature of light is. And even as far back as the Greeks, they wondered, is it more like a wave, like a water wave, or is it more like a particle, like a little rock? Well, fast forward, Newton had the same thoughts. He actually was pretty sure that light was a particle, more like a little rock than like a water wave. And he actually gave it a name. He called them corpuscles of light. The argument continues until the 1800s. In the 1800s, folks like Faraday and Tesla and others, through experimentation with electricity and magnetism, they figured out that light is absolutely, definitely, for sure a wave. And Maxwell published in the late 1800s a series of 4 equations. They're called Maxwell's equations. And we don't really get into them in this class because they're very calculus-y. So we're not going to really get into depth in those equations in this class. We're going to more focus on the results of those. But it was a fantastic triumph of physics because it managed to tie together electricity and magnetism and light and radio waves and all of these different phenomena into a tidy little thing, which was an electromagnetic wave, which is what we've been talking about for the last 15 minutes or something. And it worked beautifully. Except for a few little problems. There was just a few little details that this wave model didn't really explain. Here's an experiment that we can do that is not very well described by the wave model of light. What we see here is a photograph, but this is not a photograph that was just taken all in one instant. What this is a photograph which has been exposed under very, very, very dim light. And what do we see? If we look at this picture right here, there's only maybe a few thousand spots that on this film that have been exposed. And notice that each spot is completely exposed or completely black. As we go here, we start to really see the face, but again, it's still a whole bunch of dots. And by the time we get to this picture, it's completely exposed, and now we see it's definitely a face. What are we seeing here? What we're seeing is individual light particles striking the film and exposing it. So apparently, light is a wave, and it's also a particle. It's kind of crazy. There are other experiments. The one really famous experiment is called the photoelectric effect. This is actually what Einstein won his Nobel Prize for. The photoelectric effect is an experiment that nobody can figure out a way to describe using the idea that that light is a wave. Nobody can explain it using that idea. But if you treat light like a particle, it's easy to explain. We'll talk about that more later in the semester if we get there. So, in the 1800s, scientists conclusively determined that light was a wave. But now we move on to the 20th century, and we see the scientists conclusively determine that light is also a particle. So who's right? The answer is they both are. So light is a wave, and it's also a particle. So if that freaks you out a little bit, and you want it to either be a wave or you want it to be a particle, you got to get over it. So what do we call these? Newton called them corpuscles of light. The modern term is a photon. So a photon is a light particle. What do I mean by particle? Gosh, it's just a little chunk of light. Photons have no mass, as far as we know. They do carry energy. They do carry momentum. Oh, that's weird. We'll put that off for right now. Okay. So, the photon model of electromagnetic wave consists of three basic postulates. And the first is that electromagnetic waves consist of discrete massless units called photons. A photon travels in a vacuum at the speed of light. Okay. Each photon has energy h times f, where h is what we call Planck's constant. Planck's constant is this itsy bitsy number. And it describes how big of a chunk of energy a photon has. And the photon's energy depends on its frequency. So the frequency times this constant gives us the energy of a photon. I have here a couple of different laser pointers. Let's see if we can communicate this. And you'll see that when I shine this on here, my camera picks up absolutely nothing. So we're going to have to figure out a different way to do that, huh? Oh, that's green. That is green. Okay. That's red. So, red light has a longer wavelength, therefore a lower frequency than does green light. So while the light emitted from both of these laser pointers can be described as particles, photons, light particles, the photons in the red light, because red light has a lower frequency, these photons carry less energy than these photons do. The superposition, so that means the adding up of a sufficiently large number of photons has characteristics of a continuous electromagnetic wave. In other words, by the time you get the, 10 to the 30th or something photons per second that are coming out of this light laser pointer, the difference between the photon model and the electromagnetic wave model, there is no difference. So we add up a whole bunch of photons and we recover the wave model. That's what this point is saying. Let's do an example. We've got a 550 nanometer wavelength visible light. Let's do this example. We've got 550 nanometer visible light, and so what is the energy of one photon with that wavelength? Well, we know that the energy of a photon is given by, let's go ahead and do black. Where's black? Here's we go. We know that the energy of a photon is equal to h times f. And we also know that the speed of light is equal to frequency times wavelength. Now in this equation, in this problem, we have been given the wavelength and not the frequency. So I'm going to go ahead and solve this for the frequency and then plug it into this equation. So we have the frequency equals c over lambda. Plugging this in here, we get h c over lambda. So now we can just simply plug in our numbers. And of course, h is 6.6 times 10 to the negative 34th joules times seconds times 3 times 10 to the 8th meters per second, all over the wavelength, 550 nanometers. That's 550 times 10 to the negative 9th meters. Running our calculator, we get 3.6 times 10 to the negative 19th joules. Okay, How about this one? A 40-watt incandescent light bulb emits about 1 joule every second. How many visible light photons are emitted in 1 second? Okay, so we've seen a lot of problems like this, right? Where we have this idea where the number of packages equals the total amount divided by the amount per package. And so we're going to do that same thing here, where we get the number is equal to the total amount. Well, that's 40 watts. Well, watts are joules per second. So 40 joules per second divided by the amount per package. That is 3.6 times 10 to the negative 19th joules. And we run our calculator and we get 2.7 times 10 to the 18th photons per second. Well, that sounds like a big number. Is it? Well, to put that into comparison, the universe is something like 14 billion years old. And there is about 10 to the 14th seconds in 14 billion years. So there are more photons per second coming out of a fairly dim light bulb than there have been seconds in the entire universe. So indeed, this is a pretty big number. I think it deserves a star and an exclamation point. All right, as we just saw, a single photon of light with a wavelength of 550 nanometers has energy of 2.3 electron volts. And so, if we look at this, we see, well, what's is that? 2.3 electron volts. What can you do with 2.3 electron volts? Well, you can break a hydrogen bond between two water molecules, which means that a visible light photon has enough energy to liberate a water molecule from some water or from a piece of ice. It carries more energy than is released in metabolizing one molecule of ATP. Now notice that it has enough energy to break the hydrogen bond between two water molecules, but it does not have enough energy to actually break the water molecules apart. So in other words, it cannot separate the oxygen from the hydrogen because it just doesn't have enough energy. Now, as we'll see in just a second, shorter wavelengths, higher frequencies, have greater energy. And so something like an X-ray photon, which has a much shorter wavelength and a much higher energy, now that could break a water molecule into hydrogen and oxygen. So while light is the most common version of electromagnetic radiation, there's a whole range of phenomena that are described well in this way. So in the middle here, we've got what we call the visible spectrum. And that's what we call light. That's what is historically called light. And this is what our eyes are sensitive to, this little band right here in the middle. If we go to longer wavelengths, these act more like waves. The photon model becomes less and less effective as we go to longer and longer waves, longer and longer wavelengths. Notice also that the photon energy goes way down. So the energy goes way down as we get longer and longer wavelengths. On the very longest end of this, we have AM radio waves, which might be a kilometer long, or maybe a little shorter than that, the size of a football field, or maybe a little bit bigger. We've got FM radio waves, which are about the size of a human, maybe a little bit smaller. Classic antenna design calls for an antenna that's 1/4 of the wavelength that you're trying to receive. So if you see a GMC pickup truck from 1977, the antenna on that truck is about 1/4 of an FM radio station wavelength. Moving a little bit shorter, microwaves, that's what we use to heat our food. Those are on the order of centimeters, something like this, 6 centimeters, more or less. Moving along, infrared radiation. We actually saw a demonstration of this earlier in the semester. You and I both give off electromagnetic radiation, but our eyes are not sensitive to those wavelengths. A snake can perceive infrared radiation. So look out, snakes. Okay. Moving to the shorter wavelengths, notice we're getting higher energy here. Ultraviolet light, UV light, has shorter wavelengths and higher energy than the visible spectrum. In fact, it has enough energy that when it hits your skin, it can do a little bit of a damage, and it can give you a little bit of sunburn. Moving a little bit shorter, we see X-rays. X-rays have so much energy that they're able to penetrate the soft tissues of your skin, but they get stopped by your bones, which makes them so useful for medical imaging, because they pass right through your soft tissues, but get stopped by your bones. Now, if you've gone to the dentist lately, you know that you have to put on this lead jacket when they take your X-ray, and the technician always walks out of the room. Why? Because these have enough energy. These X-rays have enough energy that they can penetrate your soft tissues, yes, but they can also penetrate your cells. And they can penetrate the nucleus of your cell. And they have enough energy to break DNA apart, which causes all kinds of problems. Moving along, gamma rays are even shorter wavelengths, even higher energy. We see these released in all kinds of nuclear processes. It's typically, you've got to have a nuclear reaction in order to get enough energy out there to create gamma rays. They have so much energy that even just a few of them passing through your body causes major damage. They're just busting things apart, busting your DNA apart. It's a little mini explosion in your cell if it gets hit by a gamma ray, which is why they're so dangerous. Okay, moving on. Here's another way to visualize the spectrum. There's just a whole bunch of information on this slide. We're not going to talk about all of it. But, here's a nice approximate scale of the wavelengths, right? Again, we see we're getting shorter wavelengths as we go to the right on this image and longer wavelengths as we go to the left. And then, of course, the frequency, be it higher frequencies to the right, lower frequencies to the left. This is sort of an interesting little bar here. Light, of course, passes right through our atmosphere quite handily, as you know anytime you see the sunshine coming in your window. But that's not true for all different wavelengths. In fact, we look here, and there's really only a tiny window where our atmosphere is transparent to the electromagnetic radiation that strikes us from the sun. And really, the fundamental science behind the greenhouse effect and climate change is really contained in this bar right here and in this temperature scale right here. The sun is very hot, and as so, it emits very short wavelengths of radiation. Those short wavelengths of radiation, which peak in the visible, pass through the atmosphere quite easily. They get absorbed by the Earth, and the Earth re-radiates that light. But the Earth is not as warm as the sun is. I don't think you needed science class to know that. The Earth is cooler than the sun. So, the Earth emits longer wavelengths than the sun does. In fact, the wavelengths the Earth is emitting, as it tries to dissipate this energy that it's absorbed, are more in this region right here. where the atmosphere is transparent. Now, the introduction of greenhouse gases amplifies this effect and causes these wavelengths here to be even more absorbed by the atmosphere. This down here is something we're going to talk about in just a second. You've probably seen a piece of iron get hot, and maybe the end of it is so hot it's white, and then you might see a little yellow and then a little red, and then as it cools down, you eventually see it not glowing at all. The temperature that an object is at determines what wavelengths it gives off. You and I and everything around us are all emitting light all the time. As I previously mentioned, most of the light that you and I are emitting is in the infrared part of the spectrum, and so we can't see it. However, if the temperature increases, then that range of emitted light moves into the visible, and we can. And that's what is shown down on this little temperature scale. It's a little bit crude, but it gets the point across. Now, again, like I said, everything is emitting electromagnetic radiation. What is the rate of power being emitted by every object that's emitting electromagnetic radiation? Well, it depends on the temperature. And so here we see this equation. Q is, of course, heat energy. Heat per time is power. So energy per time is power. So this is the power that radiation is being, this is the power of radiation being emitted by an object at temperature T. What else do we see here? We see this is the emissivity. And that just says how good is an object at absorbing or emitting light. Something that absorbs light very well would have an emissivity of 1. Something that is perfectly reflective would have an emissivity of 0. So my stainless steel thermos might have a very low emissivity. It reflects light. Objects that do not absorb light very well also do not emit light very well. They have low emissivities, like a stainless steel thermos. Something that absorbs light very well, like a black t-shirt, would have a high emissivity, closer to 1, maybe 0.97, something like that. Again, things that are good emitters of radiation are also good absorbers of radiation. That's a constant. If I don't tell you what it is in a problem, go ahead and use 1. Now this sigma here is the Stefan Boltzmann's constant, and it's just a number. It just makes all the units work out. You don't need to memorize that. I will give it to you if you need it. Here we see 3 bulbs with increasing brightness. So here we see not as bright, brighter, and brightest. And as you go through this, we see increasing filament temperature. And so not only do we see redder colors here and whiter colors here, we also see more intensity as we move to the right. So the spectrum changes as the temperature changes, but also the power output changes. So both the spectrum and the power output change. And this is a graph that kind of demonstrates this. So at a fairly low temperature of 3,500 Kelvin, okay, that's pretty hot. We see that the peak is somewhere right here, but it's emitting photons of all wavelengths. As the temperature increases, we get more photons at all colors. That's one thing that's important to note here, is that all colors emit more photons. It's just that the peak shifts. So we definitely still get more 829 nanometer light out of this higher temperature object. It's just that that's no longer the peak. The peak has now shifted over here. And as it gets even hotter, the peak shifts farther towards the shorter wavelengths. We can find that peak with this equation right here. This is known as Wien's law. And here we see, so we can find that peak with this equation right here. This is known as Wien's law. And notice this number on top is just a constant, and we divide by the temperature in Kelvin in order to find the peak wavelength. The main thing to get out of this is that these are inversely proportional. So as the temperature goes up, the peak wavelength goes down, which that's exactly what we saw in this picture here, which makes sense. Smaller wavelengths have higher photon energy. Hotter objects have more energy to create photons. Okay, let's do a quick example. A brass plate at room temperature radiates 10 watts of energy. If we double its temperature, what will happen to the power radiated? Go ahead and pause the video and see if you can't figure this one out. I'm back. Here's the equation we want to look at. This is our temperature for the power radiated by an object at some temperature. So all of these things are constants here. We're not changing any of these. So we have power is just some stuff times t to the fourth. If we plug in the 2 here, because our temperature was doubled, 2 to the fourth is, of course, 16. And so we get 16 times the power. 16 times 10 is, of course, 160. How about this one? A brass plate at room temperature radiates 10 watts of energy. Its temperature is doubled. What happens to the maximum radiated intensity, the wavelength of the maximum radiated intensity? Well, we just talked about this. As the temperature goes up, the wavelength of the peak goes down. They are inversely proportional. And so it should decrease, and indeed it does. Okie dokie!